Hi, good morning and good afternoon, everyone. Welcome to our listeners worldwide. I am Dorit Oren, Director of Product Marketing at Gilat Satellite Networks. As many of you know, Gilat is a leading global provider of products and services for satellite-based broadband communications. With 30 years of experience, we design and manufacture cutting-edge ground segment equipment and provide comprehensive solutions and end-to-end services powered by our innovative technology. Our integrated VSAT systems are built to enable our customers to exploit the full potential of high-throughput satellites, also known as HTS. This is for both mobility and fixed applications. In today's webinar, we will focus on two of the hottest topics in satellite communications: mobility and HTS. We would like to explore the particular requirements and challenges that satellite communication faces with on-the-move applications when deployed over HTS. I am very excited to present today's webinar, Mobility SATCOM in the Age of HTS. In this webinar today, I'm pleased to be hosting Claude Rousseau, Research Director with Northern Sky Research, known also as NSR. NSR is a global market research company focusing on the analysis and growth of the satellite communications industry. Mr. Rousseau will discuss the mobility market trends and analyze the various mobility market segments. He will then pose some of the challenges that the industry is facing to be able to deliver a high-quality broadband communication experience over high-throughput satellites. In addition, my colleague from Gilat, Amir Yaffe, Director of Product Management, will be joining us to tackle some of the more technical topics that must be addressed for successful mobility SATCOM over HTS networks. Before we get started, please bear with me for a few procedural issues. First, if you would like to ask questions during the webinar, please type them into the chat box. We will take as many questions as time permits at the end of the webinar. And if there are questions that we don't get to during the session, no worries, we will make sure to get back to you later. In addition, if you miss something, don't worry, because the webinar is being recorded and we will be broadcasting it on our website soon after the webinar. Okay, so let's go over the agenda of today's webinar. I will start out with a brief introduction to be followed by Mr. Rousseau from NSR on the market trends and challenges. After NSR's market review, I will follow with a review of what we believe to be the key characteristics of the VSAT platform to best address mobility in the age of HTS. Next, Mr. Yaffe from Gilat will provide a technical review of what is required of the VSAT ground segment in order to deliver a superior mobility service. SATCOM mobility service providers should consider the following factors when choosing a competitive VSAT platform, listed here in front of you: mobility capacity management, space segment efficiency, mobility network management, and high performance and flexible terminals. After this discussion, we will then take some questions and I'll finalize with a summary. Now on slide 3, I would like to start out with a forecast by NSR regarding the mobility market revenues by vertical that you can see here in the two pie charts. Mobility verticals include maritime, aero, and land. Mr. Rousseau will discuss these specific segments within these verticals. Within each of these, within the land, the maritime, and aero, there are sub-segments that Mr. Rousseau will discuss, and he will address also the opportunities, challenges, and market growth that we are seeing. I want to point out that on a high level, we see that the mobility satellite market is expected to grow from $4 billion in 2015 to $10 billion in 2025. We see further that the historical maritime market, here marked in red, is by far the largest segment in terms of revenue today, as well as expected to be so in 2025. However, I do want to point out that the aero market is the fastest growing vertical, here in the lighter blue. It is forecasted to grow 8% by 2025. This, of course, is tightly related to the required high throughput now available with HTS. In this webinar, we will examine how the mobility verticals are impacted by high throughput satellites or multi-spot beam satellites. Look here on the right at the diagram showing the multi-spot beams. The challenge of SATCOM on the move is significantly more complex when travel goes across satellite spot beams. This is because service continuity must be ensured as the vessel or aircraft or land vehicle moves through these spot beams. The service level agreement, or SLA, has to be met no matter the load in each of the beams. Therefore, the VSAT system must take into account not only the geographic location, but also the real-time dynamics of the network. So during the webinar, we will explain why a scalable and highly dense distributed architecture for the VSAT system is key for supporting mobility applications. We will cover the need for capacity management, showing examples of how to ensure seamless continuous coverage. And the topic of space segment efficiency will be discussed, emphasizing the need to increase bits per hertz to deliver the lowest cost per bit. And then mobility network management will be reviewed, showing how to provide real-time location tracking and maintain quality of service as vessels move between beams, which of course have varying loads. And finally, we will tie the need for high-performance flexible terminals to ensure best mobility service in the age of HTS. Now I have the honor to present Claude Rousseau, NSR's Research Director. Please go ahead.
Thank you, Dorit, and good day, everyone. I'm here to present to you research from NSR over the past few years as to how this market will evolve in the next 10 years. On this slide, what we see is the evolution of the mobility market over the next 10 years. This was alluded to in one of the earlier slides. What is important to note here is that maritime markets remain the key area, and this is the historical segment for mobility over satellite. Going forward, we'll see that there's aeronautical connectivity, which will represent a much larger slice of the total market going forward. And that rests on a strong increase thanks to the advent of high-throughput satellite communications. What is interesting to note as well is that for land mobility, which is the dark blue section at the bottom of that left chart, you still see a good growth over the next 10 years, reaching over $2 billion in revenues. And again, that growth, we'll see later, is also strongly driven by HTS. Next, please. The HTS capacity demand by vertical, what we were just talking about, will reach approximately 180 gigabits per second for GEO and non-GEO HTS supply. 23 gigabits per second for land mobility, a whopping 113 gigabits per second for aero, and for maritime, which is today under evaluation, it was 46 gigabits per second the last time we evaluated this segment. So maritime demand will quickly give way to more aero HTS demand. The key question for this new type of capacity, which will offer lower cost per bit, is how to actually gain more value per bit for each end users in each of those vertical segments. Next slide, please. The high growth verticals in each of those segments are noted in this chart on the left-hand side. They are aircraft passenger connectivity, passenger vessels, and connected vehicles. Let's look at connected vehicles first. These will offer a high growth. Of course, there's a low base today, but for all trains, cars, and other vehicles, we will see that connectivity will leverage personal electronic devices brought on board those vehicles. and again, the need to be connected anywhere, anytime. For aircraft passenger connectivity, again, this is the same sort of trend that we're seeing, and this will also exhibit solid double digits growth to leverage personal electronic devices brought on board aircrafts. Passenger vessels is the fastest growing market in maritime as the focus shifts towards higher throughput demand, and especially for cruise ship. Next slide, please. Let's look down now at the maritime addressable market. We see on the left-hand side that fishing is the largest addressable market in terms of vessels, followed by merchant maritime, passenger vessels, and then offshore. But if we look at the chart on the right-hand side, the type of demand of fishing is mostly for non-broadband communications. While for passenger vessels and merchant maritime, and offshore, there's an increasing demand for broadband connectivity on vessels. And these will grow, the part in lighter blue, will grow significantly over the next 10 years as part of the total number of the broadband vessels. Next slide, please. For each segment, let's just take a quick look at what their demand types are. For merchant shipping, broadband adoption is on the rise with both VSAT and MSS. The spending on a vessel basis for connectivity is largely flat, but then there's a shift for users to want more apps or outsourced activities on board the vessels. For passenger vessels, the top-end cruise market is growing, but the bottom is quickly catching up as well. The bottom being mostly ferries. Fastest growing market for penetration for per vessel connectivity, and then again here the shift towards HTS, but at the same time fixed satellite services connectivity will remain a core part of the market for high-end leisure in particular. Fishing is mostly a narrowband market, but capacity demand there is up. Monthly revenues will remain largely flat, but what is actually the big question is what is the killer app, especially for fishing vessels that remain at sea from 3 to 4 days up to 10 days. In the offshore market, the cost is really a key consideration. Long-term spending is flat, but actually near-term it's declining a bit. Bandwidth is on the rise because each offshore platforms wants more bits per dollar. The larger production sites are driving the top-line bandwidth demand, but the growth is occurring across the segment. In short, the merchant maritime market is the biggest, but passenger vessels revenues will more than triple, as seen on the chart on the right-hand side. Next, please. In terms of capacity demand, we see a steady rise in the amount of VSAT connected vessels over the forecast period. As shown on the charts on the left-hand side, with regards to average per vessel megabits per second via VSAT, passenger vessel is really a high growth market, and that's driven by ocean-going cruise ships, and then of course offshore, which drives a good amount of capacity. And on the right-hand side, the middle chart there, we see the amount of money spent per month, and of course passenger vessels and offshore are the highest spending verticals. But what the question remains today is it just a vessel or the people on it? And then furthermore, we think that containers requirements set for each vessels in terms of connectivity going forward for things such as the Internet of Things and machine-to-machine connectivity. Next slide, please. If we look at aeronautical, which is a hot market that many people talk about these days, the traffic grew above par in 2016. The measure is revenues passenger kilometer, which grew by 6.5%. Coupled with that is commercial airplane loads nearing 80%. This means that the large part of the growth is due to rising income and discretionary spending in developed and developing countries. The result is that in-flight connectivity, or IFC, is becoming a key decision factor in passengers' airlines' choice with high expectations of quality in-flight connectivity. And most of this can be brought about by satellite. There may be some restraints on the market due to electronic device bans in the cabin. But if we look at the projections going forward, 1 out of every 3 commercial passenger aircraft in 2019 will have some form of broadband VSAT connectivity. That demand will continue and will help push over the 2019 to 20 26 period, another aircraft being connected, such that there'll be 2 out of every 3 aircraft that will be connected with in-flight broadband connectivity by the end of 2026. Next slide, please. If we look at just the capacity side, in terms of the number of in-service units on aircraft today, it's mostly L-band, and that will continue going forward as we see in the central part of the slide. But on the right-hand side, that revenue part is changed quite a bit, and we see that GEO HTS revenues will grow substantially. While the L-band play is alive and well, HTS will become the preferred solution for connectivity even over fixed satellite services. And NSR noted that in 2016, there was a ratio of 3-to-1 of contracts that were for HTS when compared to FSS. Next slide, please. Globally, this is what the picture looks like over the next 10 years as far as the market size is concerned. In blue, the 2016 numbers, and in 2026, the forecast for the next 10 years for each region. The discussion that we had earlier on about the $4 billion market growing is really spread out around the world. What's interesting to note is there will be 3 key regions, namely North America, Asia, and Europe. But again, connectivity over oceans will also be very important, such that there'll be $660 million more in annual revenues generated over the 3 oceans. Next slide, please. For land mobility, really the bandwidth is the story here. There's higher growth markets for land mobile via satellites that are pushed by smaller and lighter equipment. Also applications such as voice over IP, video and data transfer and file transfer, Again, also social media is a big part of this. Now these are becoming big revenue generators for both FSS and HTS capacity type in this market. There's also an underlying trend of diversification of products across the whole market. What I'd like to point out is on the right-hand side, the comms on the pause, which is a higher ARPU applications that is brought about by portable solutions that enable more bandwidth to be used. Well, that share of the market is in burgundy, will rise from 34% of the market today to about 44% of the total market in 2025. Next. When we talk about the challenge of providing connectivity to mobile platforms around the world in all these verticals, let's just take a look at 2 of them, aeronautical and maritime. If we look at the aeronautical traffic pattern on the top left and the right-hand side, the maritime traffic pattern, and if we put them together, we basically see that aeronautical and maritime routes will continue to push high utilization rates for HTS spot beam capacity and also FSS capacity. But for each vertical, they have their own individual hotspots. That means for maritime, Africa, and the Indian Ocean region is a unique area for capacity. For aeronautical services, North Atlantic route, of course, is key. What this means also is, let's not forget that on top of that, over land, there's a lot of land mobile users. So there's very diverse sets of verticals that have very different requirements for connectivity that will all be served by one or many types of capacity and spot beams going forward. We have to take this into consideration when looking at the efficiency of the whole network for mobility. Next. Which brings us to the challenge of the ground segment. A lot of talk has been heard about flat panel antennas. These garner a lot of interest in the past 5 years due to advantages over parabolic antennas, such as smaller and lighter weight. They're aesthetically pleasing, of course. They're increasing pointing accuracy for electronically steered flat panel antennas. And then the rate of development. Mobility is the biggest and continues to be the biggest market for flat panel antennas. Our forecast calls for 90% of the global revenues for these types of antennas to be generated by mobile satellite applications. On the right-hand side, we see a bit of the issues that are related to the efficiency parameters of flat panel antennas, such as pointing accuracy, beam steering, noise, G over T profile, the instantaneous bandwidth usage, as well as side lobe levels. Now, we believe that despite the limitations on the efficiency of flat panel antennas, Due to size, their efficiency within the entire network needs a combined development between antenna manufacturers, RF equipment developers, and satellite operators to design what we call use cases, specific solutions, and those will help maximize throughput delivered via these new and promising form factors. Next, please. In the end, what all this means for the ground segment, there's various challenges, and those challenges are for management and efficiency altogether. The mobility capacity management, of course, requires sometimes high density demand areas with multiple beams. The space segment efficiency means that transmission protocol have that carrier communications have to have less overhead or be using header compression acceleration. And then for end users that have pools of bandwidth, they need to make sure that they're able to use it efficiently over certain areas. For mobility network management, the quality of service and SLAs have to be built into contracts. Available space segment has to be there when and where required. In terms of usage, and I was just mentioning special usage, there are some that require capacity over spot beam and wide beams, and that has to be also managed efficiently. For beam to switch seamlessly to avoid drop services is another challenge. Logs to know where exactly is the users. The mobility VNO is one solution that's touted for extension of the network, and geofencing services also helps in localizing end users. In the end, we talk about also the performance and the flexibility in terminals for both VSAT and flat panel antennas. Well, of course, these are form factor dependent, and many are talking about these days of certification over several networks. These will be key to ensure that the end user has a seamless, high-quality experience. And in the end, what we're seeing more and more is plug-and-play multiple frequency terminals such that they can roam seamlessly between networks or between satellites of the same network. These challenges will be addressed now by Dorit.
Thank you very much, Mr. Rousseau, for a most interesting market review. Please stay with us until the end of the webinar when we will take some of the questions from our attendees. I would like now to discuss the VSAT platform for mobility in the age of HTS. The nature of multi-spot beams have implications for both fixed and mobility applications. This is because bandwidth is divided into many geographically separated beams, as you can see here on the diagram. These beams are adjacent and even overlapping, so there are multiple choices for beam selection for a specific service. What we mean by smart bandwidth management is to enable distribution of the load among carriers and beams. This is what will guarantee support of the expected service plans. Therefore, for service continuity in mobility applications for land, sea, and air, smart automatic beam switching is required. Notice now the animation showing an example of a commercial airline flying through beams. Of course, this example would hold for any mobility application, including ships and ground vehicles such as trains. The automatic beam switching is required to maintain this contiguous coverage while on the move. Note now, looking at the slide, that the beams can be either from the same satellite or additional satellites and can be managed by different gateways. This is a very important point. Now on the next slide, we can see the clear difference between a traditional wide beam satellite and high throughput satellites or multi-spot beam satellites. In this example, a distributed architecture is required with baseband equipment in several different gateways on the right-hand side for the multi-spot beams. With a distributed as well as a flexible and scalable architecture, the gateways can be located anywhere in the world, while the satellite data processing can take place at a separate cloud-based data center. In addition, though, it is important to note that a single global network management system must control the entire network. Note that this distributed architecture allows for dynamic resource allocation across beams as well as among applications. You see here at the bottom of the slide pointing out that this cloud-based architecture includes the chassis or the baseband equipment, the data center, and the network operation center, the NOC, in different physical locations, all in the cloud distributed architecture. Now, in addition to a distributed architecture, it's important for the baseband equipment to be scalable to support additional capacity. And this can be from either multiple satellites, as you see in the picture here, and also have the flexibility to support multiple frequencies. As you can see here, it can be Ka, C, Ku. In other words, there is no limitation, and the flexibility allows here to increase the capacity, either any band or from any satellite. Mr. Yaffe will speak more to this. On the next slide, we see another requirement when addressing mobility applications in HTS, and this is the hub density. This is true, of course, particularly for IFC, where a significant amount of capacity is required. See in this example that a traditional baseband equipment rack would not be able to support many multiple beams. High-density equipment for HTS, like we see on the right, provides the capacity required for, say, 30 beams. The equipment must consider reduction in rack space and power, and of course, higher throughput per rack. In this slide, here, the next slide, slide 24, I want to stress the service continuity that is required between regional and global service providers. The point here is that handshaking is required when a large HTS network spans across geographic regions. These are managed often by different service providers. And finally, this last slide of this portion of the presentation, I would like to point out that the VSAT platform in the era of HTS has to very much take into account economics. In other words, in order to get a significant return on investment and maximize the HTS potential, you want to be able to offset the expense of the initial investment. It's important to have a platform that can support multiple markets. The architecture should enable expansion into new markets. In other words, one platform such as the SkyEdge 2C here from Gilat should be able to support multiple applications as well as multiple business scenarios. The goal is traditionally to utilize the large amount of bandwidth. However, I want to point out that it's not only about the fill ratio, but about improving the revenue per bit. And we are seeing now with HTS that new markets have opened. There's new opportunities that have not been so with the traditional markets for satellite communication. The ideal architecture must support high growth and high revenue. And these markets are markets like cellular backhaul, but of course, relevant to today's discussion, the mobility market. So ideally, a single platform should provide support for service expansion to any fixed or mobility market. With this, I would like to turn over to my colleague Amir Yaffe for a deeper analysis of the key elements for VSAT mobility services. Just a second, please.
Hello, everyone. Thanks for joining the webinar. I will review those 4 key points in my section right now. The first one is capacity management. The second is talking about space segment efficiency. The third is how you deliver mobility network management. And I will finish with talking about flexible terminals for mobility. I will start with capacity management. As we all know, space segment is the most critical component of satellite service. And mobility VSATs, unlike fixed services, have auto-pointing, auto-tracking antennas, which enables us to use some flexibility in the way we acquire capacity. For example, multiple satellites covering the same required service area. Or we have overlapping capacity from additional satellites to enable capacity growth in high demand areas. We can also use inclined orbit satellites. Given the nature of mobile VSATs, these can track the small changes in the satellite orbit. Service may require uplinks for multiple teleports. which means we need some flexibility in the way you manage the platforms, the ground segment platforms. So when you're considering building a mobility service, you need to see how you're handling the capacity and how to tie everything together. Let's look at the building block for building a mobility network. First, you have to have a network management system, and you prefer to have one network management for the entire constellations of satellites, beams that will be comprise the service. This NMS will connect also to your OSS and BSS systems. Then you want to have flexibility in the way you choose satellites and capacity over satellites. And a number of them typically will build the service for you. Then you're going to uplink from probably one or more gateways and maybe one or more or few data centers and connecting to the internet and MPLS networks. Finally, the service is likely to have multiple beams running on multiple services, and in some cases when you're running different mobility services, for example maritime versus land mobility, you may need to use different capacity in Ka, Ku, C-band. In other words, you want to have a flexibility in the ground segment to provide a global network or regional network that enable mobility for your, suiting for your needs. Let's look at a quick example. When for your desired service area, you will want to start a service with two beams. You're going to have a capacity from one satellite provider, and you're going to uplink for a single teleport. Then later, you want to go to expand the service area. You will now look for additional capacity, and you may find it from a second satellite. You're going to now have a second uplink, and you can use the same hub to uplink for a third beam using a second satellite. Next, as your service grow, you may need to find additional capacity to provide more megabits on a certain area. In such case, you may find a more cost-effective satellite capacity from a third provider, and you may need to uplink from a second teleport. When looking at these constellations of beams, you may find that some areas now have multiple coverage options. So beam switching is not just about how you switch from one beam to another in an HTS scenario, but also how do you switch and how you define the criteria for switching from one beam to another based on priority and real-time beam load. I will review this later again. Another aspect of multiple beams and mobility is how you handle global capacity management. To effectively sell and manage HTS capacity and overlay capacity, a global bandwidth management is required. It also enables you to sell capacity to different virtual network operators or resellers across the service area. A cloud QS function, which treats the entire capacity as one, will enable you to configure group MIS area across the entire beams, even if the uplinks and downlinks are coming from different teleports and running on multiple satellites. So the concept here is to look at one global pool and enable you effectively manage this bandwidth, even though it comprises of many, many beams and many, many satellites. Next, I'm going to talk now about space segment efficiency. Space segment, as I said before, is a significant cost component for a satellite service. We all want to have maximum efficiency on it to increase the bits to hertz ratio and deliver low cost per bit. There are several factors that should be considered. The first one, which is very common and everybody looking into this firsthand, is the waveforms. How much bits to hertz you can achieve on your transmission. However, effectively to get more bandwidth savings and more efficiency, you need to look at two other components. One is the adaptive transmission, how you handle adaptive in both the forward and the return. And the third one is how do you using protocol and acceleration to increase efficiency. At the end, total efficiency should be evaluated comparing what we say router bits or the bits that running through the hub to the actual bits running over satellite. Finally, when choosing a mobility service or defining a mobility service, you need to effectively look at the terminal size. A larger antenna will provide more efficiency. A larger back will provide additional improvement in efficiency on the return transmission. So there is a trade-off between smaller antennas which cost less and larger antennas that cost more but provide higher efficiency. At the end, the business justification need to evaluate the different options. Let's look first at the waveforms. Today, everybody is moving to DVB-S2X, which is the latest generation for transmission, and with that, using HTS capacity, which is very powerful and have higher ERPs, we can get 5 to 6 bits to hertz ratio on most satellites, HTS satellites. On a return size, looking at TDMA and looking at higher modulations such as 16 QAM that they take advantage of higher G over Ts and efficient coding, LDPC, we can deliver over 3.5 bits per hertz on a return in TDMA. So that gives you a big advantage moving to an HTS satellite, a powerful satellite, and using the latest generation of modulations and waveforms. Now, once this transmission in layer 1 are there, you want to see how you manage the bandwidth, how you effectively managing in real time the bandwidth. And considering we have sites that are either in the beam center or moving to the beam edge, there is a lot of challenges how to optimize the return link for that. You'll find in mobility much more scenarios than you have on fixed sites. So the way to address it is to have really a self-adapting return carrier plan that enables you to control and have the most efficient modulation, coding, carrier rates, and forward correction to suit every transmission frame. We're looking at 4D adaptive transmission where we change the power. We're adapting for every time slot the carrier rate, the modulation, if needed the spread spectrum as well, and changing the forward air correction. This will enable to fill the entire spectrum and optimize the spectrum in any given time, leaving it fully utilized with no idle capacity left over. The end result is maximum fill factor, which improves the efficiency. Also, maximum service uptime. We'll be able to adapt the channels in real time to any scenarios and provide the most efficient mode code for every single terminal. Simple operations means that you don't need to analyze, define static configurations. The return channel is completely adaptive, enables you to have a peace of mind and really little to work on in terms of operations efficiencies to try to optimize it every day and every week. It can also serve multiple markets. You can add fixed services, for example, or using existing fixed services and add mobility. The nature of the adaptation of the return channel will enable you to work in lots of flexibility to use that capacity and make sure you're getting most income for this expense. Next, once we finished and used a very efficient transmission and very efficient adaptive channel and adaptive transmission, we're looking at how you can gain additional savings by using acceleration and traffic handling. There's a lot of packet overhead in IP. Most applications using TCP IP, they have 40 byte overheads. Web has 60 to 400 bytes requests. Voice over IP usually adds 40 bytes of overhead, and IPsec anywhere between 60 and more bytes. By using header compressions, by using acceleration, which saves some of those packets and acknowledgements, overall, in most cases, you can result in an average of 20% or more in bandwidth reduction over satellite, which means you're going to have 20% more traffic over your terrestrial link versus over satellite. These savings are significant. Now you're going to add the savings that you have from the traffic compression, and also from the way you handling the adaptive transmission, filling the megabits and megahertz that you own, and add on top of that a very efficient waveforms. The entire package will provide a significant amount of space segment efficiency, reducing your cost. I would like to touch base on mobility network management, which is a key element of any mobility service. A good network management will result in efficient operations, an efficient use of space segment, and delivering good quality service to your customers. Few key points to consider when looking at the NMS of the ground segment platform. First, you want to have one global NMS, which means that any growth scenarios in any number of satellites, beams, and regions will be supported from a single NMS. So once you've finished and have done your integration, you can add capacity anywhere. Lots of flexibility in that. When looking at scale, you want to have rich machine-to-machine interfaces for maximum integration with OSS BSS systems. Usage records enable you to also to monetize and provide gigabyte services or usage-based services. In some cases, this is a desired way to provide services even on mobility. Live maps enable you to provide visibility to all the mobility sites. You can track the sites, you can see this location, and you can have a lot of information on traffic and performance. Then you will need to also the NMS to address regulatory requirements such as location-based logs. Finally, beam switching management, which I'm going to touch base shortly now, will enable you to have an efficient way to handle the capacity. We're looking at 360 degrees management view, which means we're first looking at how you manage the satellite network infrastructure, how you provision services, how you activating new carriers, how you adding capacity. Once capacity is provisioned and network is live, you want to have good network analysis tools, performance monitoring of various parameters. This capacity should be enabled you to sell it to multiple networks, virtual network operators, to multiple customers. And the way you manage the bandwidth and the way you're managing their secure access to your network will enable you to provide the same quality of services that you can enjoy directly. And finally, network automation. It requires rich machine-to-machine interfaces, but also network processes. How you update software, how you migrate outbound, how you change carriers and migrate this information to your entire fleet. Let's look at mobility maps. It's not about the view of the maps or the beams over a map. This enables you to define a service area based on geographical area, what we call geofencing. You can also decide and define restricted areas, areas that have no transmits are allowed. You can also define transition lines. Looking at satellite performances, you can decide where you can switch based on geolocations. Service assistance is enhanced with a real-time visibility to mobility VSATs, which means that you can see the VSATs and you can retrieve telemetries and usage information. Coverage beams enable you to deliver and showing the satellite beam coverage. These are typically provided by the satellite operators and enable you to see the contours of the beams, enable you to do some analysis based on the sites that are moving. And finally, location database enables to deliver regulatory reports. You're going to have tracking of every single site, and you can see the breadcrumbs, and in the database you'll be able to retrieve information, past information from every site based on its location. Let's look closely at beam switching. what we want to achieve here is ability to have service continuity when moving from one beam or satellite, or even teleport to another beam and satellite. Most common use cases are HTS, when for certain given areas you will need to use several beams. That's delivered from the HTS architecture when high frequency reuse results in many small beams. For expansion of services, you may have some regional global coverage requirements. You may add just regular beams from wide beam satellites. And in high demand areas, as I showed before, you may have overlapping capacity from additional satellites to really cater to the needs of a certain area in terms of traffic demand. All of those will drive certain reasons to do beam switching. So beam switching decision, first is really by geolocation. That's the easiest part. We can define it based on the satellite performance, ERP and GOVTs. But you also want to consider real-time information on network utilization in overlap areas to be able to have some decisions based on the load of those beams. Beam switching really are centralized, and decisions are made by the total NMS, by the central NMS. Enable you to have full control on the algorithms, the decisions, the configurations, and make changes centrally that will propagate to the entire fleet. Let's look again at an example we've shown before, when we have 4 different beams covering a certain area. You can see there's a lot of overlapping. Okay, so how do you switch? How do you make decisions on switching in this such scenario? So first, you're looking at satellite performance figures. That enables you to really have the decision on the edges of the service area. But in the center of the service area, there's a lot of options. In some cases, 3, sometimes 4 different beams covering the same area. So when VSATs, mobility VSATs, are moving to those areas, they will need to have some more smarts. And these smarts exist in the NMS when he sees the traffic. The NMS has the information, real-time traffic information from the entire network, and we'll be able to make decisions based on traffic and beam priority. In terms of defining the service area, beams are merely an RF propagation. They basically propagate until they fade away. In some cases, you will need to define a service because of other reasons. It can be service differentiators because of service pricing between, let's say, land and maritime, or some regulatory that requires in-country landing versus out-of-country traffic landing. Those will require you to define a geofencing or a geographic service area. This is available through the network management, enabling VSAT to switch or to stop service when they're moving from one area to another. Another scenario is roaming. You as a service provider may have service in certain areas, but you want to expand, or your customers want to have service in adjacent areas or different areas. And since you don't have capacity over there, may not have equipment over there, maybe it's not enough business there, you want to have an ability to have a roaming agreement with a partner. This enables the two network management system to talk to each other and have VSAT moving from one service provider to another, still providing you visibility. Let's look now quickly at high-performance terminals. A key component of a mobility service is ability to have some flexibility in the terminals. There are many uses for terminals. It depends on where you want to go in terms of services. You have terminals for trains, for maritime, for aviation. There are different terminals that catering to different market segments. There's a lot of variety of field-proven terminals out there. Antenna systems. Gilat has, those as well. Modem installation option means, how your terminal is being installed. It can be a card form factor that's integrated to another device. It can be a rake-mounted unit or a standalone unit. You want to have all those options available on single VSAT technology and platform. For modern performance and modem specs perspective, you want to have very powerful modems and have DC and AC options, rack-mounted options, and count form factors to have the integration. Next, you want to have flexibility in the way you connect the modem to different antenna systems, mobility on the move antenna systems or on the pause antenna systems, which are used for basically quick deploy situations over a vehicle or land. Finally, for high-speed scenarios such as high-speed trains, aeronautical, and maybe high-speed boats, you require Doppler compensation. This will be able to deliver the frequency and timing corrections to be able to maintain the link and communications under very high speeds. With that, I will pass the microphone back to Dorit for Q&A and summary. Thank you very much.
Thank you, Mr. Yaffe, for a technology review of what SATCOM mobility service providers should consider when choosing a competitive VSAT platform. We still have a few minutes, so we'll take some questions, and then I'll summarize the webinar. Just a moment, please. First, here's a question for NSR. How much of the FSS KU band market today will be moving to HTS for mobility? Can you please take this, Mr. Rousseau?
Yes, definitely. There is definitely going to be a migration from FSS to HTS. Now, how big is that going to be? We have made some estimations, but by now, all in all, there's not a real set percentage. We know that there will be some end users that will still roam between FSS and HTS, and we see though that the impact on the FSS capacity demand will mean that there will be less demand growth going forward for FSS, but much more HTS demand growth. The absolute numbers, we don't have one specific one, but as you can see from one of the charts that we showed on HTS capacity demand by each of the verticals, that part of HTS is growing fast, and the FSS part itself is not growing as fast, but it will continue to grow because of the various use cases as we just mentioned and as was demonstrated.
Thank you very much. We're running out of time, so I'll just take another question here about the flat panel antennas. The question reads, flat panel technology was mentioned by NSR. How much is Gilat involved in this technology? I'll take this one. Actually, Gilat is a market leader in flat panel antennas, initially with the VSAT low-profile antennas. Gilat develops and manufactures flat panel antennas for on-the-move applications, including on land, sea, and air. And in particular, we have recently launched our dual-band Ka-Ku antenna for in-flight communication. Also, I want to add that Gilat is making progress with our phased array antenna with electronically steerable beams. As a matter of fact, Gilat was selected by Airbus to develop a more efficient IFC antenna, this phased array antenna. And this is with funding by the Clean Sky 2 research program of the European Commission's Horizon 2020 program. And as we're running out of time, I'll move now to the summary slide to summarize this webinar. So what we did in this webinar is that we heard from Mr. Rousseau from NSR about the growing opportunity for SATCOM on the move and about the particular requirements in the age of high-throughput satellites. We discussed the required VSAT platform that is needed to best address multi-spot beams in a smart and scalable and flexible way. After that, we drilled down into mobility capacity management with a focus on the required seamless utilization of capacity from both the local and global service providers. Then the space segment efficiency was discussed with the purpose of delivering the lowest cost per bit, and this is by increasing, of course, the bits per hertz. We then went to discuss the mobility network management at length by Amir. This is a key component of the solution that must deliver real-time location tracking and maintain quality of service as vessels move between beams that have varying loads. And finally, we noted the high-performance VSATs are likely to enable the required service. These terminals need to be tailored per market, and they have to have an open architecture that will enable third-party integration. And that is the last point here on our summary. I'd like to let you know that you can find more information on our website, www.gilat.com. And we do invite you to contact us and tell us your needs so we can best support you with your mobility applications in the age of HTS. I'd like to conclude with that and urge you to keep in touch. I would like to thank our guest speaker, Mr. Rousseau from NSR, as well as my colleague, Amir Yaffe. And of course, I would like to thank you all for attending. As I mentioned, the webinar is being recorded and will be available shortly on our website. Enjoy the rest of your day. This concludes the webinar. Thank you.